Alright, hello and welcome. Today is April 23rd, Thursday, and we are live. And so as you know, the school schedule's changed up a little bit. We're going to a 4-day week, and this no new stuff on Wednesday is going to affect our calendar as well. So we are officially off the rails on our calendar. Off the rails, so we have to reestablish our ground a bit. Things will be pushed back by every day we're missing. We're kind of pushing things back, which means we'll have to cut out a little bit from. Well, we will. I mean, it was pretty much planned anyway, but we'll have to cut out some from the last unit, the magnetism unit. Other than that, you'll notice things will be pushed back. The mastering physics has been pushed back a little bit, a couple of days, 2 days, because we're missing 2 days this unit. And therefore the test is going to be pushed back, etc., etc. Every day we miss. So by 2 days for now. We're off by 2 days. And it seems my system is acting weird and very unstable. Something is wrong with my RAM. So, and I can't fix it right now because that would take too long. So I'll have to fix it. Hopefully it lasts until I'm done streaming, and then I can start looking at trying to fix it. But if the stream does go down, don't worry. If I'm not back within 5-10 minutes, then I suppose you can work on your mastering physics. But let's hope that it doesn't crash. I think it is working now. Yeah. Okay. So I guess I'll start by going over a few mastering physics problems then. Ooh, my dashboard everything is crashing. This is not good. And we'll start with question number 1. A couple of conceptual questions from chapter 21. And I see that a few of you are already finished. Wow, you guys are way ahead of the game. Here is question number 1. Mastering physics. Ooh, purple. Mastering physics number 1. And that has to deal with resistance. Where R, we know that the resistance formula R is equal to this resistivity constant rho times the length L divided by the cross-sectional area A. Right? How do we see lab 3? Is it? No. You missed the announcement. We are behind by 2 days now. So, behind by 2 days. Yeah, the Wednesday thing is going to affect our schedule a bit. Let me pull up the calendar. Let's take a look. Yeah, so the project was canceled, of course. So lab will be tomorrow. Lab tomorrow. Okay, so we know that R is resistivity times length times cross-sectional area. So if you had an object like your resistor, so let's draw a nice cylinder. So the cylinder is some sort of resistor. Is this a cylinder? Something doesn't look right there. Whatever. of course, it has a certain length, L, and if you take a look at the face, it'll have a certain amount of area, and the area of the face is what we use. So, yeah. Snap. Yeah, this is, I don't know if this is gonna work. Something happened where I can't. Something weird is going on. The whole thing is unstable. Everything, like everything from Google to just my Streamlabs to, I don't know, everything's just crashing. Let's see if it's okay. It's not back. Oh, here we go. I don't think it's not a virus. It's my RAM is unstable, so it was unstable at 3.2 gigahertz at 1.4 volts. I downclocked it to 3000 megahertz at 1.38 volts, but I think one of the RAM sticks is giving me issues, so I have to tear it apart and then fix it up, but I can't do it right now. I thought it was working last night, but clearly it's not. So yeah, that's that. All right. Anyway, while we're still here, resistivity. Let me know in chat if it does go down again. I'll continue to fix it up. I should do like a PC enthusiast channel where I teach you how to like build your PC and like mod it and overclock it and stuff. That'll be cool. Who would be interested? Raise your hand. No one? I'd be interested. Oh, okay, Dennis. All right. Oh, we got three. All right, cool. Yeah, so I can teach you how to like overclock, install like fans and coolers, talk about airflow, all sorts of cool stuff. Yeah. And did you know like you can actually like literally just as a student you can just get a job, fixing computers and stuff, and you can make tons of money. Kuya Casey says he's gonna build his own system over the summer. Nice, nice. Uh, $700 budget. Yeah, dude, that would be a really cool thing. Like where we do like budget builds. If you know what like PC Part Picker is, there's like a website that basically you can pick up your part and look through pricings and stuff at various websites all together, and we can probably like do cool stuff like that where we say, all right, what's your budget, and then here's our limit, and then we try to put together the best system for the whatever job you're trying to accomplish. Hopefully, it's not just video games. Oh, it's for school homework, of course, right? Resistivity. Resistivity. Resistivity is a property, a material property. Resistivity is a material property. Material property meaning that it is dependent on what what physical material, what element your resistor is made up of. Right? Different elements will have different resistivity values. Okay, so things that conduct very well. Remember, conductivity and resistivity are inversely related. Things that conduct very well, like metal and stuff, are very poor resistors, right? So of course, copper is pretty good at conducting, therefore has very low resistance. Become a PC YouTuber. Oh yeah, like my dream would be to like become someone like I don't know if you guys watch like Jay's 2 Cents, and there's some other guys who do it. I feel like, man, I can easily, do that type of stuff. But those guys are like sponsored by big giant companies like Nvidia and Intel and stuff, so they get like free Linus. They get free stuff though. See, like as soon as like the new 3080 Ti comes out, I'm sure like those guys would get like um, free video cards to test out and benchmark. Like all that stuff is so easy. Like I don't know, I can easily do it, but I don't have the connections yet. So one day, hopefully, when my YouTube channel grows, and then I'm like 50, 60 years old, and then I'll become a tech guy. uh, so it depends on the material, of course. Now the other thing is that there are ways to change the resistivity value of a certain element. Well, I shouldn't say element, of a certain circuit element. There we go. Yeah, the dream. Can we get hashtag the dream trending right now? Okay, so anyway, as I was saying, of course, changing the physical dimensions, like the length and the area, could affect your overall resistance value. Um Resistivity would be, I would have to swap out different materials. Typically, resistors are a combination of materials like ceramics and other types of materials that are put in there. Um, Depending on the combination, you can control how much flow you want, right? The other way to control it is through heat. Okay, heat makes it very chaotic inside. Right? Heat is pretty much chaos. It's the combined total kinetic energy, the root mean square of all of your little particles that are jiggling inside. So all particles are moving around. They kind of wiggle and vibrate, and all of that energy, the vibrational energy, is what we call heat. Right? And heat increases. Oh no, my water bottle is empty. This is not good. Uh, Heat increases the resistance. Oh, I should say resistivity, really. I'll just say resistance. Oops. Okay. The hotter it is, the more chaotic it becomes inside here. And so when charges try to flow through, here's a little green positive charge. Remember, current is the flow of positive charges. And so when it tries to flow through, all of that chaos that's inside here kind of hinders its movement. So less charges can. So imagine these being like vibrating little particles, and they get in the way. They get in the way of this charge from moving forward. And so the heat will decrease the flow of current. And this leads to other topics in that traditional light bulbs. So I should call them filament light bulbs. Filament light bulbs do not follow Ohm's law because of this heat difference, right? So heat equals more resistance. Yes, heat equals more resistance. And in that a cold bulb has low resistance and a hot bulb has high resistance. So what happens with filaments is that when your light bulb is off and no current is flowing through, the metal that is inside the light bulb is cold, and when it's cold, the resistance is very low. And when it's very low, when you know that because V equals IR, you're going to get pretty much high current. But as soon as you turn it on, okay, as the current starts flowing through the metal, now the metal starts heating up. So the resistance actually changes as a function of time, in that as it's on, it increases its value really quickly. It jumps up, and so the initial current that initially flows through the filament wire decreases once it's nice and hot. Remember, when resistance increases, the current must decrease. Okay. So when I say it doesn't follow Ohm's law, only because the R value is changing, and so you can't really measure the resistance of a light bulb by using an ohm meter. Remember, when we have to use ohm meters, we have to disconnect the element and then touch the two ends of your circuit element to measure resistance. But because the cold light bulb has a different resistance value than a hot light bulb, you can't really measure it. So what you could do is to turn it on and then use an ammeter to measure the current, use a voltmeter to measure the battery or the voltage, and then divide V divided by I, voltage over current, to get the resistance value. So you can find it experimentally, but you can't really measure it directly because of this heating phenomenon. Okay. Yeah. So why do light bulbs kind of go out? Why do you blow out light bulbs? Ever wondered when a light bulb blows out? Okay. Usually when you blow out a light bulb, it happens as soon as you turn the switch on. When you flip the switch, you might get like a flash, and then the light bulb is gone, it's dead. That's because especially during like winter time, when it's cold, especially when it's cold out, you're going to get lots of current going through that filament, so much that the filament melts, kind of like our fuse thing that we were talking about last time. So remember how fuses melt when a certain amount of current or more current passes through their limit. Similarly, a cold light bulb might have too little resistance, and so when the initial current comes in, it's way too high and it just melts the filament, and so the filament breaks. It's very rare that once a light bulb is on, it's going to go off. That's because once it's on, it's hot, and then once it's hot, the resistance value goes up, so less current actually flows through, which is very interesting. All right, so let's take a look at number 2 now. Number two is an ammeter can measure current as small as 12 picoamps. Mastering physics, numero dos. 12. So my number is 12. Your number might be slightly different. Chat, what is pico? Chapito, what is pico? Pico. What is pico? If you remember, nano 9, so nano is 9, And pico is the one after nano. Oh, we got one. It is -12, yeah. The great monarch King Henry died by drinking chocolate milk made in Poland. So this is 12 times 10 to the -12 amps. All right. How many electrons per second flow through the wire? All right. So here's a kind of a charge type question. Now we use the formula for current. Current is the amount of charge you get, delta Q, per time, delta T. Right? An amp, 1 amp, is a coulomb of charge per second. So I want to know how many electrons flow through. First we have to figure out how many charges. So delta Q, do the old swap-a-rooney. Multiply both sides by delta T. Delta Q must equal the current times the time. How much current is flowing times how many seconds have passed. Oh snap. Here we go again. Why is this happening? Is there an update for Google Chrome maybe that I don't know about? No, my Chrome is update 8. Man. Alright, as I was saying, the charge is current times time, but you have to have everything in SI units. And so make sure you convert your time to seconds. Your current should be in amps. Then you can multiply. Alright. Once you have this charge, now you need. Actually, let me see if I can. Once you have this charge, now you need to find how many electrons. So you can divide this number by the charge of 1 electron to get the number of electrons. Right? So Q, the total charge, divided by number of charge of an electron. Oh no, this is not correct. It says electrons per second. Electrons per second. Okay, so they don't want total charge. Oh. If I have total charge, this is. Sorry, you can't do it this way because they don't give you time. If I don't have time, but I want electrons per second, that means my time is essentially 1 second, if you will, if you do it that way. Every second, 12 times 10 to the -12 coulombs of charge passes through the wire or through the ammeter. Okay, so if I just want for electrons per second, electrons per second, we can just divide the current by the charge of the electron. Because if I did current divided by charge of an electron, this would give me number of electrons per second, right? Because I is coulombs per second. So I is equal to Q over T, which means amps is equal to coulombs over seconds. So if I were to divide this by charge of an electron, remember E is the elementary charge. It is crashing. Today's not a good day. Maybe it's crashing because well, I don't know, why is it crashing? Is it because I'm switching windows? Is it really annoying? There we go. So 1 divided by E, so if I divide this by E, I get amps per number of electrons, and so the E is equal to 1.6 times 10 to the negative 19 coulombs. This will give me electrons per second. Okay, the coulombs cancel. So we have number of particles per second, and the number of particle is the electron. Alright, let's try to get through this before it crashes again. Was that number 2? Yeah, that was number 2. Number 3, so number 2 divided by E is 1.6 times 10 to the negative 19. Number 3, okay, let's go back. There we go. Number 3 says a charge of 12 coulombs flows past a given point. If the current produced by the charge is 0.15 amps, what is delta T? So number 3 is using the same current formula, where current is well, I'm not controlling it, so I can't control it. Mastering physics number 3. Same current formula, delta Q over delta T. And so if I want time, then I can just multiply, I can solve for time. Time is equal to delta Q over I. There we go. The old swaparoo. So delta Q is the charge, so that's given. Charge, and just divided by the current. Okay. And let's do one more, and then we'll do a complex circuit, and then we'll be done. I want to end the stream as soon as possible, because we are not very stable today. How much charge passes through a 12-volt battery that does 37 joules of work? So now we have an energy question with number 4. How is energy related? So this is the electrical potential energy. So if you look through your flippy, you'll find electrical potential energy somewhere. So the energy, so PEE, electrical potential energy, or the work done by your charges, PE, is equal to the charge Q times the voltage V. I should use delta. And so if I want to know how much charge, Q must be equal to the energy divided by the voltage. Yeah. So in these mastering physics problems, you're using everything pretty much. So look through your notes, look through your flippy. You'll find all the formulas. So charge is equal to energy divided by voltage. The work energy in joules. This is your voltage. In volts. In volts. All right. All right. So that should get you started. And let's do one example, I suppose. Complex circuits. This is carrying over from last time, where we had combinations. We'll do a different combination. Perhaps this one. Whoa, we have 4 resistors. Let's call this one R1, R2, 3, R4, V. So we've learned our lesson. We want to use 3 sig figs, not 2. We'll make this 12 volts again. Let's go and let our... let's make a chart. So R1, R2, R3, R4, rec. This is V total, the battery. Then we have V1, V2, V3, V4 to worry about. We also have some currents. No! What happened? Oh, we're still alive. Oh, okay, never mind. Yay! We're still alive. I1, I2, I3, I4, I total. And if for fun you can do P's. P is power. Power is current times voltage. IV. So how is the rec situation in this circuit? Alright, so current comes out, gets to a junction, then it has 2 paths, this way or this way. Well, that's the last drop. Need to refill. And so these 2 branches are parallel to each other, but within the branch we have 2 resistors, so we have to take care of that first. We have these 2, R1 and 2, and we can see how whatever current splits up, whatever portion goes to the first branch, these two resistors, R1 and 2, actually share the same current. And they have the same current passing through them. And the same story can be said about resistor 3 and 4. And so 1 and 2 are series, 3 and 4 are in series. We can redraw this. With just 2 resistors now. Okay. This is the red one. It's R1, 2. The combination of 1 and 2. And this one is R3, 4. So R1, 2 would be addition this time because they're in series. And R3, 4 would be also addition, R3 plus R4. Okay. So look for patterns. When they are right next to each other, and you know the same current goes through them, then they are in series. Whoa, whoops. Let's give some values. let's see, let's do 2 and 4, and then 3 and 3. So that means 1 and 2 make 6, and then 3 and 4 also make 6. Oh, yay. So they're both 6 and 6. And now we have 6 and 6 in parallel. What's the parallel of 6 and 6? Okay, these double lines and the parallel symbol. So R12 is parallel to R34. We use the parallel rule. 1 over 6 plus 1 over 6, which gives us 3. Okay. All right. So, what else can we say? The current splits up, but these two branches are parallel to each other. Therefore, they must have the same voltage as the battery. Let's do something called a loop rule. So the loop rule, and then we'll put it all together tomorrow. The loop rule tells you how the voltage will drop as you go around a certain pathway. Let's draw 2 pathways, a red one and a green one. So the red pathway, imagine a charge flowing in your system. It comes out of the battery, and when it gets to this fork, the red pathway goes down the 2 red resistors, and that's your pathway. The other pathway, the green pathway, instead of going through 1 and 2, it'll skip that point, it'll keep going, goes to 3, 4, and then we'll get back to the battery. So these 2 pathways, this is called a, there's someone called the Kirchhoff, and it's his loop rule. So here's our loop rules. And the loop rule, what's nice is that it works for even more complex circuits where you have different elements, not just resistors. You can have other things in a circuit, and the loop rule still works, which is really cool. And the loop rule tells you that when you go up a battery, so here's rule number 1. I should use black. Let's use black. Going up a battery gives voltage, so you're adding voltage. Going through a resistor loses voltage. So subtract minus V. And then the most important part, the sum of all voltages around a loop equals 0. Sum of all voltages sum of all voltages equals 0. Okay, so let's see if we can write some loop rules. Here's the red one. The red one starts with the battery. So the battery gives me V volts, which is 12. And then as you follow along the red pathway, you lose V1, the voltage at resistor 1, because anytime we go through a resistor, we lose some voltage. And then you lose some more at V2. at resistor 2. I'm okay, thanks for asking. V minus V1 minus V2. And once we pass through resistor 2, well, we're done with our loop. We're back to the battery. So then we get to our third part. It says sum of all voltages. You know, yes, it says sum, but we are adding negative numbers because we're losing voltages at the resistors. So V minus V1 minus V2 should equal 0. And then for the green loop, I should probably use purple. Some people can't see. Uh-oh, there's kids outside. What are they doing? Hey, kids! Get off my lawn! I feel like some old dude yelling at kids. I'm changing the colors because some people can't see red and green. So here's our purple. And what's a good color? Purple and blue? Blue. Purple and maybe they can see orange. I don't know. It'll be slightly off color. Purple and orange. Darn kids. They must be from Florida or something. In the orange loop, let's do a chat. Can you do a loop rule for the orange pathway? So follow the method. Remember, when you go through a battery, you get voltage. When you go through a resistor, you lose voltage. So what is the equation for the orange, the new orange colored pathway? Ooh, 15-week grade there, dude, next week. Great. Well, if I go around this pathway, of course we start with the battery. The battery gives me V. And then I'm going to subtract the amount that is dropped at each resistor. At R3, we will lose V3. And at R4, we will lose V4. We're always losing voltage whenever we go through a resistor. The resistor heats up and uses the electrical potential energy. So we're losing our potential. Equals 0 because we're done with the loop. See? And this will of course let you build other equations. You know, V1 is I1 R1, and V2 is I2 R2, etc. But there's also it also tells you that you lose all 12 when you go through each branch, right? So V is equal to V1 plus V2, and V is also equal to V3 plus V4. Okay. The other thing we can do is find the total current and do current splitter rule, which is something we learned last time as well. The current splitter, let's see, I total is equal to the total voltage over the total resistance, which gives me 12 over 3. Yeah, I used nice numbers that divide well this time. So 12 volts divided by 3 ohms. There we go. 3 ohms, 12 divided by 3, that's 4. So that's 4 amps of current. Okay. Now, when that 4, that's the total current, so that 4 amp is coming into our junction here. This junction right here. And so I don't know how much time I have, so let me finish up this problem and then I will have to take apart and try to fix my system. We found I total. I think I total was the last thing you saw. I total was 4 amps. And then using the current splitter rule, you're able to find the current in each branch. So for example, I see that I34 is equal to, remember it's the opposite branch in the numerator, so the opposite branch is R12, divided by the sum of each branch. So the sum in the first branch R12 plus the sum of the second branch R34. Oh god, no. Yeah, this is not gonna happen. All right. So use the current splitter rule to find the current in each branch, or just look at it. Since each branch is 6 ohms, it's going to split up 50-50 to 2 amps of current goes through each. And since 3 and 4 are in series, they have to have the same current as well. Go ahead and finish up this problem. We will look at our answers next time. If you can't solve it, please leave the answer of I1, 2, 3, and 4 in the comments below, and I'll check those comments once I put it on YouTube. You can put the comments down below, and then I'll check those comments, and we can go over it tomorrow. Thanks for watching. See ya.